Yes, welcome back to Easy Gates, Gate 22 Instrumentation Paper Solution. The next one is the question number 41. One of the important, interesting problem happened based on a PID controller. Okay. Yes, that's a problem given. So we have a PID controller that is employed to stabilize. It is given as stabilize the control, stabilize. Okay, to stably control. Okay, a plant with a transfer function P of S. So we can take it as GP of S. So we have a plant, a second order plant, okay, having no integrators. That's the beauty of this problem. It is controlled by a PID controller means, so you can take the controller transfer function this way. It is going to be Kp plus Ki by S plus Kd into S. This is the better version. There is another version of PID controller that won't help you, that will trouble you actually. So refer this. Okay. So that's only tricky point of this problem. So what is given is in this. Yes, now you will understand the next statement. Okay. So without taking this structure, you won't understand clearly. So we have a PID controller that is employed to stabilize a control plant that is having a transfer function this. Okay. So that is our system to be controlled. So we have a controller that is PID. So we have a proportional gain that is increased by a factor 2. That means is increasing Kp twice. That means Kp doubles. And the integral gain is also okay. The integral gain is increased by a factor 3. So it is increased by a factor 3. Derivative gain is not changed. That means what factor is talking about? So this is doubled, whereas Ki is increased 3 times. Then the derivative gain doesn't get changed. Okay, it remains unchanged. Given that the closed loop system continues to remain stable with the new gains, the steady state error in tracking ramp reference signal is the input command is a velocity command. It's a ramp command. Okay, so given that the system remains stable, yes, that's very important point. Otherwise, you can't apply the steady state error analysis. Steady state error concept is valid only when the system remains stable. Since we have a PID, so we are adding a controller to tune the performance. It is important that you are looking for desired performance, but still there must be a desired stability. And ESS concept is valid only when the system remains what? Stable. Okay. So, but still you can check it because KP value, KI value, KD value not given, you can't investigate stability by using RH. Okay. So therefore, yes, given the hint that the system remains stable, you can straight away proceed for the steady state error analysis. Yes, that's a closed loop system. So I thought of giving without exact system. So I planned for this. Anyway, system is given now. Take the system. It is 1 by S plus 1 into S plus 2. So first what you need to understand is first you need to go for the steady state. You need to go for the steady state error. Assuming it's a ramp input, you need to go for the steady state error. What is the steady state error? Fundamentally, ESS is equal to A by KV. Okay. So straight away use it. That's a velocity command, go for the velocity error constant. So what is KV? KV is equal to limit S tends to 0, S into G of S, H of S. So before that, you have your PID controller. That is the PID controller is KP plus KI by S plus KD into S. Better you take the LCM and keep it ready. If you take LCM, it is going to be KP into S plus KI plus KD into S square will be there. So that's your P divided by S. That will be the controller transfer function. So what is G of S? G of S is the whole forward path transfer function. So what is our G of S? It's a product of your controller transfer function and the plant transfer function. So get the whole G of S. The whole G of S is going to become what? GC of S into GP of S. GC of S into GP of S. GC of S already determined, that is KP into S plus KI plus KD into S square, the whole divided by S. Okay. So into the system, that is 1 by S plus 1 into S plus 2. That's what given. Okay. So this is your GC of S. Now let us find the velocity error constant. What is that? Limit S tends to 0, S into G of S, H of S. So what do you get then? If you multiply S with this, so then it is going to get, so let me do it straight away here. Okay, so it is going to be limit S tends to 0. It is S into KP into S plus KI plus KD into S square. Okay, the whole divided by S into 1 by S plus 1 into S plus 2. So what is getting cancelled? This S and S will get cancelled. So what's your KV? So KV is going to become, letting S equal to 0. So KP will vanish. KD also will vanish. So then the result is going to be KI by 2 you will get. That's going to be the KV. So therefore, what's your steady state error then? So then let me continue. So ESS is equal to A by KV, and KV determined. What is the KV we have determined? It is A divided by KI by 2. So slope of ramp is not mentioned. Let me take it as it is. It is going to become 2 times A by KI. That's your steady state error as a function of, okay, integral gain. Okay. So this is what we get as a steady state error. He said in the statement, KP is increased by a factor of 2 and integral gain is increased by a factor of 3. Okay, what is the question? The steady state error in tracking the ramp signal becomes, okay. So the statement is, it is a MCQ problem. Let me pick the choices, 1 minute. Yes, that's a point. So it is given Ki increases by 3 times. Okay, if that is the case, what will happen? If K increases by 3 times, your ESS, old ESS is what? 2 times A by Ki. What is the new Ki? It is going to become 3 times. So it is ESS is equal to 2 times A divided by your Ki. That Ki is going to become what? 3 times Ki means. So this is your old ESS, call it as 1. This is the new ESS, call it as 2. Then it is going to become ESS divided by 3. That means your error decreases by a factor of 3. Okay, it is decreasing by a factor of 3. Okay, so Ki increases by 3 times. So error decreases by 3 times. Okay, so that's a easy problem based on a PID controller. The point is this. So KP and KD are not coming into the play. Who influences your error constant? Okay, so due to ramp command is only your KV, that is only influenced by KI. So KI alone influences your steady state error, as KI triples your error becomes 1/3 of your old error. So the best choice is option C. Okay, yes, that's a correct answer. We'll update you with the next problem. Thank you.